quantum machine learning and IBM Global Qisit Summer School. So why is this important, this Qisit Summer School? Well, IBM is one of the market leaders in quantum computing. They have more than 30 quantum computers available nowadays. A lot of them, they are available for free, so everybody can just connect and experiment. They have produced some very large and reliable computers comparing to the competition. They have a very developed research program. If you look at the research papers, for example, you will see a lot of them, they are actually published by IBM researchers. They have also produced and they are developing the framework, which is called Qisit. So Qisit is a framework that you can install basically on your laptop, do the development of quantum algorithms. There are already a number of applied quantum algorithms that you can just use and practice, learn. So their program is very advanced. Also, their education program is very advanced. This summer school was third in a row. So the first summer school was dedicated to basically quantum researchers. The second one was already virtual. It was last year because of COVID situation, but there was really a lot of interest. And this time there was 5,000 people actually who registered for this Qisit Summer School, and the Qisit Summer School was focused on quantum machine learning. So I think it is very interesting because of the lectures that we were able to actually follow. So here you see all those topics that we worked on. I highlighted in yellow those that are directly related to the quantum machine learning, and those white, they are introductory topics or indirectly related to quantum machine learning, but also very important, to understand the more specific topics. So one of the introductory talks that I find really very relevant for this period where the quantum computers are still small, we are talking about 80 qubits. We are talking about, in case of IBM, machines, and the other competitors, they are not much better. The coherence time is quite limited, which means that the quantum states will remain as they are, as you initialize them for up to 1 millisecond, and then afterwards they will degrade. So if your algorithm takes longer than this, then you will just get a rubbish. So basically these computers now in this era, they are noisy, and that is why this period is called NISQ, noisy intermediate scale computers. In this period where computers are noisy, it is very important to understand what this noise means, actually, how to model it and how to factor it out from your algorithms, how to do the kind of error mitigation. Now, this is not the same like error correction, because error correction is having a fault tolerant quantum computer. Error mitigation is coping with this imperfect technology as it is nowadays. So this was the talk given by Zlatko Minev. Zlatko is by origin, he's Bulgarian, he works at IBM. He is one of great physicists. Actually, you will see if you search for his name that he has discovered some phenomena that were not really perceived by other researchers, like continuous behavior somewhere where it was believed that it is strictly discrete. But okay, I mean, this is just a separate topic. He was talking for our quantum machine learning course. He was talking about the noise. And here what you see on the screen is ideal behavior of one small circuit that you will see here on the left-hand side. So what I have here in this circuit is just one gate that will change the state from 0 to 1, from 1 to 0, 0 to 1, 1 to 0. So in the ideal world, this should produce this kind of result. So we have here 1 and -1 because the expectation value of this quantum state 1 with respect to the Pauli matrix Z is -1. So that is why we have 1 and -1, not 1 and 0. But you see that basically this here is the ideal behavior, and this is what you expect to get from a quantum computer. And this is what you will get if you run your quantum algorithm on your local simulator, if you run it on your laptop. But what you get actually from the quantum computer is something like this. So, and now the question here is whether it is really here 20, between 20 and 40 X gates that you lose your state, and then it gets another period here in that you are still getting some results, or how it behaves really, if it is after 30 or not. It depends on the computer, it depends on the machine itself. This can vary, but not that much. And this is basically the results of the quantum computer, which is running the same circuit. So here what we can see, for example, is that there are different sources of this noise. There is this projection noise. This is random variations. So these are, this curve here is not smooth. You will see the fluctuations. And why is it so? It's just because you are going to perform your experiments for a limited number of time. So if you do this infinitely, if you have infinite number of shots in one run of your circuit, then you will get a smooth curve. But as we are limiting always this for at 1,000 or 10,000, then you have variations. The next important source of noise, it's this SPAM, which stands here for state preparation and measurement. So what does it mean? Well, if I just go back in my chart, you will see here that we have strictly 1 and -1. And here it is a little bit less, because our measurement devices, they are not perfect. So there is a probability that instead of measuring and giving us the state 1, sometimes it will give us the state 0, not really the state 1. So this probability actually is calculated here, and then you will have the impact because of that, measurement device imperfection. You will have the result which is not ideally 1. Then we have things that are even more dramatic. We have this behavior which is a kind of cyclical. So you can imagine that there are two trends here. You can identify there are two trends. This is a coherent noise. Without this incoherent noise, and we would imagine that it's kind of periodic function. Go it like that. So, and what is this? Well, basically, when you do the quantum gates like that, these are rotational operators. This means that basically the quantum state will rotate around the x-axis. So the quantum computer, the controlling mechanisms, basically they will rotate. So, and this rotation is also not perfect, but there is always a kind of little angle that is either added to your rotational operator or reduced from the rotational operator. As a cumulative effect, basically you have more and more. Cumulative adds up, so you will get your state and the result of it has to go like that. Then this incoherent noise, it represents actually the phasing effect and relaxation effect of your quantum state. As I mentioned, currently the longest time of these superconducting qubits with IBM machine is one millisecond. And after 1 millisecond, it means that you just very low here, practically you will lose. So these are main sources of the noise. And what you need to be aware of is that this can dramatically disrupt the results of your quantum algorithms. So that is something that there are some modeling exercises that you understand to model this noise, to understand the probability distribution of all of these different sources of noise so that you can actually factor it out from your results. It helps. It helps a lot, and that's a mechanism actually used nowadays and that we call quantum error mitigation. So this was one interesting lecture that I appreciate very much, because as soon as you want to work on the quantum computers, then you deal with this effect. So the next important topic is how to build quantum.
So Sasha, sorry, but there's a background noise, regular background noise coming up. I don't know what it is.
I think I'm going to put everybody on mute. I hope it is better now. Thank you, Bora, for pointing this out. So talking about building quantum classifiers. So as we know, in machine learning, we have classification problem. So most of the cases we are talking about how to classify the data, the input data according to different classes. So what we can see here on this side is basically just a little illustration of what quantum computers can be used for in the context of quantum machine learning. So this here, C, stands for classical information. And this second letter stands for what kind of platform we are using to compute, to implement the classifier. So this is just a traditional classical machine learning. On the other hand, we have quantum states, just some kind of quantum data used maybe for quantum physics, just physical phenomena from physics, which we implement on quantum computers. We can also use our classical computers to implement the classifiers and to help to develop some kind of machine learning algorithms for the quantum data. Or we can, and this is the case that we are interested the most, is actually how do we handle classical data on quantum computers. And this is actually what we are calling also quantum enhanced machine learning. So I mentioned NISQ era, so these are noisy computers, and this determines basically how we implement machine learning algorithms. So these machine learning algorithms here, because of the noise that we mentioned, because of the limited time that we have to implement our quantum algorithms, they are of hybrid type. So basically they rely on one hand on the quantum computer, but then we are going to extract the information, we are going to perform the measurements, and the results that we extract, we are going to feed into the classical optimizer in order to optimize the parameters that we use in the second iteration of our combined hybrid quantum machine learning algorithm. So there are different things here that we have to pay attention. Well, basically on this illustration, we see how it looks like. So these are our qubits. Then we have to encode the data, and then we have our model. So this is our model that we designed, our machine learning model on a quantum computer. And of course, here we don't see the output, which are the quantum states that are measured, basically represent some classical output. So first question is, how do we encode the data into quantum machine learning model? So we can do it in different ways, like a basis, which is basically when we have just the binary data, 0 and 1. So we will encode it into the input states. We will initialize the qubits in 0 or 1. So this is very simple and will not really be able to encode much of our input data if this data is complicated. So the next one is actually the amplitude. So what is the amplitude? We are going to create a circuit. When we pass through this circuit the input data, as the result, we will get the amplitude vector. So we will measure after multiple experiments, and we will get this amplitude vector. So the output of this circuit, this amplitude vector, has to correspond to our data. So then it means that actually we have to design our circuit with rotational parameters, with everything, so that it produce this amplitude vector is the result. A third one, angle, is quite intuitive. So we can imagine that each of these qubits here can be rotated, the state can be rotated, and our input data will be used as the indication of the angle. So we are rotating, but at what angle? So in this case, it's quite easy to understand what it means. So basically, if we have a input vector of 10 data attributes, then it means that we were going to just convert this into the angles and to implement this as a rotational operators on 10 qubits. So this is a angle-based data encoding. And higher order encoding, this is quite interesting. It allows actually to encode very complicated data through these functions that we can't just simply encode using basis, amplitude, or angle encoding. How it works, where basically we are going to put all the qubits in the superposition. Then we are going to use angle encoding. Then we are going to use multi-qubit rotational operators, which basically, if the qubits, they are already in the superposition, which will bring all these qubits into entanglement. And we are going to repeat this block multiple times. So which is this is very interesting. The fact that we are repeating this block of rotational parameters, entanglement, then again and again and again, this actually allows to have very rich representation of our input data. So when the data is encoded, we have to develop this this model. So this is actually a discussion about the variational models. So how do we create this this model? Again, we are talking about single qubit and multi-qubit rotational and control operators. So here we will see the difference in the expressivity of different gates or circuits with different complexities. So this here, if we have just identity, we can't, our model doesn't represent anything. So it doesn't have any representation capacity. If we use just simple and single gates here, so it will be able to sample the data from a limited set of our quantum states. If we use multiple gates with different parameters, then we will be able to sample much larger, from much larger space of quantum states. Yeah. So this is where people are experimenting a lot, and there are different proposals. This is an interesting research paper that talks about, well, some samples and how they behave. So there are some different measures, actually different metrics, how we can measure the expressivity of these models here. So X, Y, Z, you know, these are 3 dimensions, and this it means that this is rotating around X-axis, this is rotating around Z-axis, and then of course behind this there are the angles, how much you're going to rotate each of these qubits here. So it turns out that these circuits 4 and 11, they are simple and they are quite expressive. And this circuit here, number 6, it is one of the best that is actually recommended. It demonstrates very high expressivity. So you will see that basically we have rotational parameters, but in each of them we have also these entanglement gates. So this is creating entanglement between qubits. And this is also important because without that, well, we will not be able really to capture a lot of the correlation in the input data. So this is very helpful. And there are some, in this research paper, it's quite a good discussion about the metrics and why it is so and how to experiment further with all of that. So this is how we develop a model. So where do we fit this model? Well, we have said that we are going to encode our data, then we are going to develop our model based on some parameters, and then we when we run all that algorithm, then in the end we are going to measure. So we are going to measure all these quantum states. As a result of the measurement, we will receive a classical data. So this classical data actually is helping us to identify, as a first run, what class we are getting. So like in all other machine learning algorithms, the first run will just give a completely wrong label, but we are going to use this prediction, this received label, calculated label, in order to calculate the value of our cost function. And then we are going to optimize our parameters, to update these parameters and to feed them again into our model. So this cycle here will run until convergence. So the question is now, when we measure, how do we actually, when we measure the state and we get this classical data, what do you do? How do we represent actually the label just based on that? So there are some ideas on how to excite the labels. It's based on parity. Like, for example, if we have a state which is 0, 1, 0, so, you know, two zeros, 1, 1. So, you know, 0 is pair number. So we are going to just say, well, this is our label +1. So, and if we get a state 1, 0, 1, so, so in this case, two digits out of this bit string, which are 1, and then we are going to include, just to label this as our -1 label. So this is one very simple way. And the second one, which is very interesting to just think about, is we are measuring only the first qubit. So we have multiple qubits, we can have dozens of these qubits, but we are just measuring only the first qubit. And this is enough. So, you know, this is quite amazing. So you don't need to measure the others. Why? Because you put everything, the whole quantum system, into entanglement. So even if you do the rotational operators on the last qubit that you don't measure, basically it will have the influence on the quantum state of the first qubit, which is entangled and that you are going to measure. So this is quite interesting insight actually that we. Oops. And then, of course, as I mentioned, we are going to use this information to run the optimization of classical computer. So then the question is, okay, well, the gradient descent, you know, we have to calculate the gradient of our quantum circuit. How do we do that? There is a very simple rule which says, okay, and which is called parameter shift rule, which says, okay, we are going to run this circuit with our angles, but we are going to add a little shift. We're going to add to this angle just a small value, and we are going to measure it. Then we are going to run the same circuit, but these parameters, we're going to reduce them a little bit for the same shift. So, and we are going to measure that. So then we are going to deduct, to subtract these two values, to normalize them, and this is the value of our gradient, which if you visually represent what the derivatives mean, the functions, so you will see that this is practically the same thing. So this is a practically easy way how to implement gradient over quantum circuit. So there are some, of course, there are some more sophisticated advanced rules, and this is, for example, the latest one, which is even better. But yeah, that's something quite advanced now. So this was the session that I explained about how to build a quantum classifier. And as I explained, well, this quantum classifier is depends on some parameters that we are going to optimize using a classical computer. And this is how basically we have to do now until sometime in the future, in 10, 15 years, hopefully, there is the indication that we can really have fault-tolerant large-scale quantum computers. So in that case, I mean, with the algorithms that we will use, they are going to be different. But now, in this intermediate stage, we have to live with this kind of hybrid algorithms. The next session is about the optimization and using this quantum approximate optimization algorithm, which is a special K of variation quantum eigensolver. VQE is typically used quite a lot for quantum chemistry. So this is talking about Hamiltonians. These Hamiltonians, they are the operators that are actually expressing the ground state energy of a molecular system. And in this case, well, they are a nice basis for developing this quantum approximate optimization algorithm for optimization use cases. And this is also based on the variation quantum circuit. So this QAOA algorithm can be used to optimize and to resolve optimization problem of a specific case, specific optimization cases, which are called QUBO, quadratic unconstrained binary optimization problem. So it means that this binary, it means we are talking about binary decision variables, yes or no, 0, 1, 1, -1. Unconstrained, it means that, well, normally all optimization problems, they are subject to some constraints that we have to respect. So, for example, we want to pack the boxes in one truck, so the constraint is the size of the truck. So in each of the optimization problem, we find these constraints that we have to respect. The QUBO is basically the model that expresses the problem in an unconstrained way. But constrained problems, they can be transformed into QUBO. So there are different ways. Some of them, they are already QUBO problems, and some of them, they are very easy. Instead of this, considering the constraint, we just put it into the quadratic or linear part of our optimization, the function that we are optimizing. So this is not a problem. I mean, just this definition of this QUBO. And QUBO problems, they are NP hard. So it means that exponentially, depending on the size of the problem, it takes more and more resources to resolve them, and from certain size of the problem, it become intractable. So it turns out that many optimization problems that we can encounter in the real world can be expressed or transformed to QUBO. For example, the set partitioning problems, this is a kind of clustering, like unsupervised machine learning. We have assignment problems, packing problems, constraint satisfaction problems, etc. So, and for typically you will see a lot actually of these demonstrations, they use this max cut problem. This max cut problem is good for education, doesn't have really much use in practical examples, in practical real-world problems, except I would say in telecommunications, for example, that there are some very special use cases. But it is nice illustrative example of how this QAOA can resolve QUBO. So, by the way, I have found also this interesting research paper which talks about a real example, real use case of object detection. So, object detection, you know, in visual recognition, that when you have object detection, basically it will frame each object with a framing box. And the problem is if you have a lot of people that you take an image, so your algorithm very often is going to put some redundant framing boxes. And you want to get rid of this redundancy. And well, this is important. I mean, maybe you think, well, if you see some videos and for some trivial examples, it's not so important. But you know, typically the cars, self-driving cars, they have to identify. They need to know exactly how many objects are in front of them. So it is important. So this removal of the redundant framing boxes for different objects. It is done by optimization algorithms. And this is where the researchers, the authors of these papers, they managed to apply this QA/OA. So how do we do that? Well, max cut can be expressed using this weight matrix. We will just then convert it into mathematical representation, mathematical model of that problem. We see already that we have a cost function. And starting from there, we can also convert this into our cubo cost function. So when we have the cubo cost function, it turns out there is already this Hamiltonian operator that can help us to resolve this optimization problem of that cost function to find minimum of the cost. So it is quite straightforward. So talking about cubo, we can express that through the Hamiltonian operator. And when we have a Hamiltonian operator, well, basically then we will define our quantum circuit, how to get the result from that quantum circuit, which will be the solution of our optimization problem. So here you see, for example, we are talking about Zi, Zj. So these are, you will remember when I talked about Z axis, rotation about Z axis, or Z Pauli matrix. So this is here the Z. Izj, so you will see later, but these are controlled 2-qubit controlled Z gates. Here we have simple Z gates, and this is what we are going to implement. So how to do it? Well, there is a trick. So and we have to understand what is happening behind. So the thing is, in order to implement this on quantum computing, there is a kind of theorem which says, well, if Hamiltonian of the system is a ground state and we modify it very slowly, the system remains in its ground state. So, okay, well, this is a very difficult now to explain in very short time. But the thing is, the trick here is that we are going to prepare a very simple Hamiltonian, a new Hamiltonian, very simple Hamiltonian. Then we are going to initialize in the ground state, and we are going to change it slowly. We're going to change it slowly in order to grow towards our cost Hamiltonian. And this, we have seen the cost Hamiltonian, basically it is our, expresses our problem, our optimization problem. So how do we change from one Hamiltonian to another? Well, it is this trick here. You see that we have a composite time-based Hamiltonian, which is the summation of two Hamiltonians, our very simple Hamiltonian, which at the beginning will have the full value, the value of 1, when the t is 0. And our cost Hamiltonian will be 0. But then over time, as we go through our quantum circuit for different iterations, then this t here will grow, and our mixer Hamiltonian will go down, will reduce slowly until 0, and our cost Hamiltonian will grow until it just represents our, it contributes fully to our composite time-based Hamiltonian. So this is actually the trick that we are using in order to change slowly from our simple mixer Hamiltonian to our Hamiltonian, cost Hamiltonian that represents our optimization problem. And as the result, we will get the solution of that optimization problem. So how do we define this mixer Hamiltonian? It's very simple. We just bring all qubits in a superposition state, and this will create the highest energy state of mixer Hamiltonian. So this is the highest energy state. And this is actually, here we are talking about ground state. which is minimal energy state. This is highest energy state. So, you know, in our computation, we're just going to change the sign, and instead of highest, it's going to be minimum. So that's basically, this helps us to get this mixer Hamiltonian superposition state, which will represent the highest energy state of that small and simple Hamiltonian. So we have to repeat this procedure p times. And here you see how it works. So basically, we have qubits in the superposition, which is we bring the system in the highest energy state. Then we are applying our circuit to implement our cost Hamiltonian, then mixer Hamiltonian, and then we have to do this p times, p iterations, to bring this value of t, you know, from 0 to 1 through p different iterations or layers. In this case, we are talking about layers. So this is the implementation of the cost Hamiltonian here. As I mentioned, you know, there are some Z gates, single qubit Z gates, and there are some entanglement Z gates here, 2 qubit Z gates, as we have seen in the definition of our cost Hamiltonian. If you remember, we have Zi, Zj, and we have then individual Z operators. And this here is basically our mixer Hamiltonian again. So we have to, this is just one block, and you see here this block repeats many times. So, and of course, at the end of these blocks, here many times, of course, not just this one, we will measure, and then when we get that, we will extract the mean of cut values, then we will going to run the optimizer to optimize our thetas, and these thetas, basically, these are parameters of the of the cost Hamiltonian. So how does it work in practice? Well, basically, the problem is that it improves over time, but there are no performance guarantees. So basically, this method will work, you know, but it's still not proven that you will get those, you know, quantum speed up that we are talking about, that we really are looking forward to have comparing to the traditional optimization algorithms. So it's a quite active area of research where researchers, they are experimenting with different things that are helpful. So we can't say that this method should be discarded. You know, this is not the case. And eventually, with larger computers, with more reliable computers, and with an advance within this domain of with some new ideas, this QA/OA will be able to provide relevant quantum advantage comparing to the classical optimization algorithms. So what are these new ideas? Well, for example, use a classical optimization for the initial state in order to get to the initial state for the mixer Hamiltonian. So this is something that helps. So then take only the best measurements. So this here, you see that it is taking the average value. So the thing is, we can apply some heuristics, take only the best measurement outcomes, and this will accelerate. We don't need to go through too many of these iterations until the convergence, so it can accelerate this process. And what was noticed actually is also very helpful, that some smaller sub-problems, if we go through the optimization algorithm, go to the end, so the parameters that we have optimized eventually, they can be reused. They can be used for the larger, because there is much similarity between the parameters of the small scale problem and the large scale problem. So these are different ideas actually that are very helpful, and so in the near future, hopefully will bring some new insights. Next important topic is support vector machines. So we are talking again about classifying problem. So in the classifying problem, we want to classify the data between two classes. So here you see that we want to find this boundary, decision boundary, that will separate our two classes. So we can do that actually by going through different algorithms, classifying between these two different classes based on the input data. But what is actually much smarter to do is to find what are these vectors here that go through the nearest data points. So we are actually looking for the lines that are going through the nearest points and are trying to maximize this margin. So in the end, what we will get are basically the vectors that we call support vectors. And the algorithm behind it is called support vector machine. So basically, we are not looking directly to find what is this line, this linear decision boundary or linear hyperplane, if we are having high dimensional space. We are looking for what are those vectors that will actually represent the highest margin between what we will call in the end as this decision boundary. So by looking indirectly, we will be able to detect what is this linear decision boundary. So this is one important feature of support vector machine. Another important feature of support vector machine and why it is so popular is basically that we have a problem that some data is not linearly separable. So this is a very small example here. You see that this data is lying all on the same line. So here linearly, we can't really say, well, where this decision boundary should go. We don't know that. But for example, if we add some new features to the input data, and if we bring this data to a higher dimensional space, then we can conclude, well, okay, well then in this case, we can find in this higher dimensional space, we can find what is this hyperplane, what is this linear hyperplane. So, and this is actually being done by adding, transforming our initial data set into a higher dimensional data set. How do we do that? By adding some features. And what are these new features? They basically, we don't invent new features, and we can't do that. What we do is basically we use some combination. We use some mathematical combination of the existing features here in order to add an additional dimension. So you can imagine here, if we know that this is the middle. So what we are going to do in this case is maybe, we are going just to deduct, this is a value, I don't know, here, 5. So we are going to say x minus 5 squared. So this will, if it is squared, this will immediately bring it up. But this here will be still, this point here will be still 0. So, this is the intention behind adding all these additional features here that will basically bring this, the whole model in higher dimensional space. So I mentioned looking indirectly at this classification problem, not looking directly at what is this decision boundary, linear decision boundary, but what are those support vectors. And this is, this model here, mathematical model, is what helps us actually to identify what are those support vectors. Also, at the same time, taking into account those new features. And here we have feature functions or feature vectors. So the thing is, calculating directly these feature vectors here, if we are talking about thousands, 1,000-dimensional space, this mathematical operation can be very difficult to perform. Just to find what are those feature vectors, if we have thousands, and then each of them, they are kind of mathematical combination squared or some quadratic function of that. So it is going to take really a long time. So, another trick, what is used basically is we are not going to calculate the values of these feature vectors. We are going to find another standard function that is helping us to identify the level of similarity or the distance between the data points. So, and this is what is called kernel. So when we are talking about support vector machines, normally we use this kernel trick in order to help to be able with support vector machines and these kernel functions to classify data in this nonlinear space. So we are talking about primal formulation, which is very simple. This is our classification. And then we are looking at a dual formulation of this problem, which is helping us actually to do a shortcut, to find, to do the optimization and to find these support vectors in much easier way and computationally with less resources. So this here, we can see one of those kernels. You know, I said we are looking at some kernels, some functions, standard functions that will help us to identify what is the similarity. So this is one of them, this RBF kernel, which is quite standard way how what we use in this support vector machines models that work very well. So then the question is, okay, well, how do we use quantum computers for the support vectors? So we have seen here this variational quantum classifier already. So we are encoding the data, and this already we can say, well, we are encoding these additional features. Yes, we are encoding the features. So this is here not just the input data, this is a feature function. And here is our model. So our variational model. But the thing is, if we run it, and we have seen basically from discussion about this quantum classifiers, that this part here is not able to perform very sophisticated things. So why? Because we have noisy computers. We can't really have very deep circuits. So all in all, this is going to parameterize just a small subset of our possible hyperplanes. The idea is basically is to implement kernel, one of those standard kernels, or to find what is the quantum kernel that will be able to use as a kernel, like in our dual formulation of our optimization problem, in order to identify what are those support vectors. So, and this is actually a new algorithm, quantum kernel estimator. So here, what we can see, this is the feature function. This is a feature function, but inverse. This is just the inverse feature function. And this is the circuit which represents our kernel estimator, or calculate, is calculating the value of our kernel function. So how do we use it? Well, basically, we are going to run our state through the first part, through this block here that represents our feature function for one data point, xi. And we are going to run the inverse of that feature function on the data point, another data point, xj. And we are going to do this for all combinations of I and j. So this is here what we are doing in order to create this matrix. And this matrix is our kernel matrix. We will then use this kernel matrix that we obtain from the quantum circuit. We will use this matrix. This is a matrix with classical data. We will use this matrix, Kij, and push it through a classical optimizer in order to identify what are our support vectors, alphas in this case. So this is actually what this quantum kernel estimator is doing. And then, of course, if we want to get the quantum advantage, which means that this is relevant, this is not possible to simulate classically, then these feature functions should be hard to compute classically. This is something that is very difficult to find. And that was one of the conclusions of this session, that it is very difficult to identify what are the right quantum kernels that will provide this quantum speedup. So just a bit of summary. So we have seen that the feature function will take a data point from original data space and map it to higher dimensional feature space. Kernel function is a kind of standard function, and this kernel function, it takes two data points in the original data space, and it returns what is their similarity or the distance in their feature space. So this is very interesting characteristic of the kernel function. So in order to implement support vector machines, we are looking for some standard kernel functions. And for the quantum support vector machines, we want to find out what is the best quantum kernel function. So that is actually the main question, how to choose quantum kernel function to ensure that we get to the quantum speedup. So there is a discussion of how to identify the right quantum kernel function. For example, this here is just some trivial circuit where we use different rotational operators on each of the qubits. And these rotational operators, they are parameterized here. So this is not really, it is very easy. It is trivial to simulate classically. So quantum kernel based on such a circuit will not give us any benefit. I mean, in the end, it will work, but the thing is, why should we use quantum computer for that? That is the question. So how do we make it more interesting? So we can add some more complexity. Experiment with adding the entanglement, the swapping, adding another layer of rotational parameters. So this is one way. Another way is a repeated depth. So we have one kind of block here with a superposition, with entanglement, with rotational parameters. So what we are going to do is repeat this several times. And this will increase the complexity that this kind of quantum kernel can't be simulated classically. So this is there is a lot of work actually to experiment with, like I showed those circuits, like what are different circuits that provide better expressivity. So there is now also in this field also a lot of experimentations and comparing what are these circuits that will bring the most value when we are talking about quantum kernels. So the main conclusions from this is basically that quantum kernels can only be expected to do better if they are hard to estimate classically. But this is not sufficient. This is necessary condition, not sufficient condition. And what other condition is important for these quantum kernels? So basically, we need to define these quantum kernels so to follow the structure of the data. And that is these are the main takeaways from this session about quantum support vector machines and kernel methods. So it has to be hard to estimate classically, and it has to follow the structure of the data. And there is an example of this discrete log kernel. This kernel was designed based on Shor's algorithm that is able to recognize the underlying structure of the numbers, of the integers. And for example, this I just cited here, this paper, where you can see, for example, how this D-log kernel was developed. So, which is a promising news, positive news out of all of this is this D-log kernel. It demonstrates exponential or super polynomial quantum speedup. So, and this is actually one instance of this group of quantum kernels. So this group of quantum kernels and the whole framework that we are using to develop quantum kernels which exploits the group structure of data, where this discrete block kernel is just one instance, it shows actually that we can find also other similar kernels. We just have to follow the same framework. So this is actually the most promising direction now in exploring and experimenting with quantum kernels. Okay, I'm aware that we are running over time, but I mean, if anybody is constrained to leave the call, I mean, it's get upset. Just I think I will try to compress this a little bit, but there is one topic more, and this is neural networks. So we know about neural networks, we know about deep learning, and there is a lot of work actually on how to implement those neural networks on quantum computers, and we are then talking about quantum neural networks. So basically, one of the interesting takeaways is, when we are talking of parameterized circuits, when we are talking about variational quantum circuits or quantum algorithms or quantum neural networks, they're all synonyms. So basically, that's you can't say that there is a substantial difference between variational quantum circuit and quantum neural network. So they are working on the same way. It's just the terminology. We just want to highlight that we want to replicate or to implement neural networks on quantum computers. So there are different ways how this can be implemented. Some of these models, basically, they are just given here as illustration, and they are very simple. So this quantum perceptron is an interesting area of study, because this is the basic building block of neural networks. There's a lot of work there, a lot of papers, a lot of different ideas on how to implement this perceptron. It is important because when we know, how to implement perceptron, then we can just add these building blocks and create large models. So what is interesting here is that all of this is implemented entirely on quantum computer. Now, we are not talking about kind of hybrid neural networks where, one part you will have initial layer, the second layer, third layer, you will have on a classical computer, and then you take just one part, few layers, and then you implement this on a quantum computer. So then it's this is a hybrid model. This is also what people are doing. Here on this slide, we can see entirely quantum neural networks. So the main problem with quantum neural networks, the quantum neural networks, they are universal function approximators because they have this non-linear behavior. So we are relying on activation functions between each layers in order to introduce this non-linearity. And this non-linear behavior is very difficult to implement on the computer. So that is a main difficulty. And there are some ideas, and you see some of them here, to use quantum Fourier transform, to use this schema, repeat until success, or just to use the measurement, because the measurement is stochastic process. So basically, this is something that we can use like through this ancilla qubit to add this nonlinear behavior. As I mentioned, this quantum neural networks, they are universal function approximators, and also there is a paper that theoretically proves that also quantum neural networks, they are universal function approximators, which is really great news, because then right implementation of quantum neural networks will be able to, it's foundation of modeling very complex things from the real world. So what was an interesting insight and interesting takeaway from this session was basically that you remember when I said we have encoding the data, then we have our variational model, and then we repeat this several times. We repeat this block several times. So this is actually what is happening there. So if we have only one Well, in this case, we have 1. So 1 block will allow us to simulate a kind of the sinusoidal periodic function. If we have more of these blocks, if we repeat, then what we'll be able to implement more complex periodic functions. And this is even more visible here. So this blue here is just 1 repetition, 1 block. So this is what we can model. If we repeat it 3 times, we can model more complex behavior. If we repeat 5 times, then we can model even more complex behavior. So eventually, repetition of these blocks allows us to express very complex behavior of the input data, of the probability distribution of the input data. So this is a great insight that one should use actually in order to build quantum neural networks. So this was a model of how to build quantum convolutional neural network. You know that in the convolutional neural network, basically you are reusing a lot of parameters. You know, you are reusing parameters from different layers. And this quantum convolutional neural network is inspired by the convolutional neural network, and actually it shares parameters across layers. So it means that the number of parameters we have to train is reduced. So, and it works very well. So basically, this is an interesting concept in quantum neural networks. Dissipative quantum neural networks. This is another model where we have, you know, we are just dissipative is because we discarding. Once when we bring a new register with these 4 qubits, we bring a new register, we entangle it with the first register, then we continue working with the second register. We just discard those qubits of the first register. And here you see basically that figuratively that this would represent our second layer. You know, this is like our first layer of our neural network. This is our second layer, and then we can add like that more and more layers. And of course, we'll be able to reuse. Physically, nothing prevents us to reuse this, this first register later. A main problem in training quantum neural networks is the gradient descent, what is called as a barren plateau. And you can see this here. This is a normal behavior of a normal optimization or normal cost function, where you can descend through this valley until you reach your local optimum. So global optimum is not guaranteed, but at least local optimum, local minimum. But in case of quantum neural networks, it is very frequent with many qubits and the deep circuit that you get on this plateau here, where the gradient is, the change of the gradient is very small. So that is the problem. Vanishing gradient descent that is in quantum neural networks is even more pronounced. So there were a lot of experiments on what is happening and how to avoid it. And this is these are some recommendations. You see that here, for example, we are talking about global cost function and local cost function. So this L. So what is local and global cost function? Global cost function is when you measure all qubits. Local cost function is you measure only the first qubit, only one qubit. And this helps, actually. So measuring just one qubit helps. Why is it so? I mean, for me, it's a bit, I didn't get into all these details, but recommendation is to use local cost function instead of global cost function. And another thing is not only that, the problem is when we add more qubits and when we add the depth of our circuit. So that is where we can we start experiencing this barren plateau phenomenon. So these are the results of different number of qubits and iterations. For this particular example, we see that the local cost function, it degrades a little bit, but that's not dramatic. So yeah, this was basically the intention of discussion actually about the training problems of quantum neural networks. So overall, this was a lot of sessions. There were a couple of other sessions that was just because of the time constraints, I was not able to prepare and to present like generative models. There is also in quantum machine learning also topics around reinforcement learning, which is a very interesting domain of machine learning, so quantum reinforcement learning. So overall, this school was quite good. For 2 weeks, each day there were 3 hours in labs. Well, the thing is, there are quite a lot of lecturers. A lot of lecturers which they use different notations, they talk with different vocabularies and things like that. So that was a bit challenge. I mean, when we are doing these courses, when I'm giving the courses, for example, we have to make sure that that we have the same vocabulary so that students can follow, do the transition from one session to another. So that's a challenge. And there was an interesting also talk at the end. It was a panel discussion where IBM has gathered really some experts, leading experts in the field, like Maria Schulz. If you search for her work, you will see some of the books that she published. She's a researcher and professor teaching quantum machine learning. So she was a bit, pessimistic and saying, "Well, okay, hold on, guys. Let's, we are all enthusiastic, but probably quantum machine learning, knowing that we have noisy computers and that we are still looking for those right quantum kernels and having a problem with the training of quantum neural networks. So this will not be really be able to provide the advantage over classical deep learning, based on GPUs or supercomputers for the next 10 to 20 years, she said. But it is a general case, and that, there are going to be some special situations where particularly this discrete log or D-log or quantum Fourier transform can be applied with quantum machine learning. And she said, well, everybody's looking like a number of qubits, and is there a quantum speed up or not? So that's important, but maybe the whole community should stop and work on a tool set, on a basic tool set, and to create these basic building blocks of the quantum machine learning, which can be a completely different discipline. It doesn't necessarily need to be replication or implementation of what is in the classical machine learning on like it is on quantum computer. It can be done in a different way. And then she said, well, this is basically what needs to be done, a kind of fundamental research about what is this basic building block of the quantum machine learning. Okay, I think this is the end of my talk. Are there questions? I hope you can unmute yourself.
Sasha, Bora here. I will have to step out for another call. Thank you very much for this very interesting and condensed material. We will keep in touch outside.
Okay.
Thank you very much. Bye-bye.
Thank you, Bora, for being here.
Sasha, Tomasz is here.
Tomasz, yes.
Thank you very much for the presentation. It was really great. And then what came to my mind is that what I heard from PsiQuantum CEO is that they aim for 1 million qubits because he says that there is no evidence that NISQ machines will provide any quantum advantage. And however, instead of 10 to 20 years, they are aiming for like something like between 5 and 10 years to have those 1 million physical qubits. So what is the feeling at IBM about this statement that NISQ will not be useful at all?
It's, you know, I worked at IBM until end of June. So it's quite recent, actually. So, and we had these discussions in our internal meetings. Some of the use cases, for example, machine learning is maybe not the first one to provide, you know, to provide the benefit through the quantum speed up, quantum advantage. But what is expected most is actually quantum chemistry and optimization problems. So it is true that there is a lot of research being done, a lot of experimentation, and a lot of doubts. Well, we are going to a lot of obstacles, but there is some optimism, realistic optimism that some specific use cases will be able to be implemented and to provide a quantum advantage. You know, we are talking also about the first real quantum computer that IBM is preparing for 2023 with more than 1,000 qubits. They are already building this computer. It is on IBM's roadmap. So with more than 1,000 qubits, it is expected that this will bring some useful things. So what are these useful things? How many they are going to be? 1, 2, 5, 10, hundreds? I don't believe there is going to be many, but there are going to be some of these use cases with quantum advantage.
And one more question. So you mentioned this 1,000 plus qubit computer from IBM. So when that realizes, and then we have a quantum kernel which will provide some useful results, then maybe it will be the case that we don't want to bother simulating that via classical computers because it will be just such a complicated problem. I mean that it can be that we simply cannot prove maybe that it can be simulated via classical computers, and even if we can prove that it can be simulated, maybe we just won't bother because it would be just too complicated to implement. What do you think about that?
Well, the proof, I think that it's going to be done rather theoretically. Yeah, because you're right, you know, how to try to simulate it. You know, there are going to be some standard models how you can try to simulate this, but eventually it's going to be more kind of theoretical work. So this quantum kernel, what it consists of, why we use these gates, and what is expected number of or order of time or operations needed in order to be able to simulate it. Well, for me, I think that actually having a lot of qubits and improving the technology, where I was talking about 1 millisecond, hopefully in 2 years, I mean, the engineers will be able to extend also this even more. This is promising, but still it might not be really enough, you know, to be able to develop something really very useful because of the noise. We have seen that. So until we have fault-tolerant computers, then it's always going to be a trade-off what you can do, and if these 1,000 qubits they are enough, or or not. And in addition to that, the problem of the design, how are you going just to develop a kind of small circuits and then to scale them, to have like replicate, copy, like this module, we are going to copy that. Or we are going to try to design, invent something really that is suitable for those large scale computers. But there are a lot of challenges there. I can't.
Sasha, just one question. You explained quantum neural networks. Is there any course, or did they go through any practical examples of how this could be or is currently being used? I mean, I'm thinking more in terms of financial services and trading, for example. I mean, that's an obvious route. And do you know of any practical examples of that?
Well, in terms of finance, basically, we can use machine learning. There are some ideas, rather the ideas and the research work on using reinforcement learning for the trading to learn these policies. And then there is experimentation actually to add quantum classifier on top of that to accelerate or to help speed up the process of learning this policy. And in case of trading, so this is very important because we want to save time. And if we are able to resolve many calculations at the same time on quantum computers, this is valuable. There are some ideas on how to use quantum machine learning or quantum neural networks for finance, but most of the financial use cases, basically, they are very specific. They don't include quantum machine learning. They're not based on quantum machine learning. So they are like generating samples, and these samples, they are very important in financial industry. So these samples, according to a particular probability distribution, it can't be generated classically. It's very difficult to generate high quality data set, artificial data set classically. So this is where there is a lot of work on quantum algorithms that can produce this kind of sample data. Then there is another case of risk analysis, portfolio optimization. So derivative pricing, the optimization of transaction settlements. So these are the use cases where there is quite a lot of work. Some of them, they are based on QAOA, basically, and some of them, they don't use this Hamiltonian that we have seen, but a very similar way of trying to optimize.
Correct. I mean, most of the trading patterns, what they're using is basically pattern recognition, right? Even now, even.
Well, okay, in that case, but I'm not aware of any specific practical use case that was developed for financial industry or pattern recognition, because as I think that we have seen, most of this work is still kind of, learning, experimental, and things like that. And especially with the current computers, the largest computer is now with 60 qubits, 70 qubits, something like that. And of course, I'm sure that companies, large banks that have access to these computers, they are already testing some of it. But I don't think that this is something that these banks are going to use as a production system. Now, all these banks, they have started already, large banks, they have started their projects since 1, 2, 3 years in order to learn what quantum computing is about, to learn how to develop quantum algorithms, which way, and also to identify what are the best use cases that they can play with. So they are rather 2 examples, very small examples where they are testing and then checking, well, okay, this is interesting, it works. What is encouraging actually that all these experiments, they show that quantum computing works, that they can implement this on quantum computers. And that, in perspective, you know, this is a kind of promising way ahead. Okay, thank you all.
Can I ask something more? That so for 2021, IBM wants to build a 127 qubit machine. Do we have any insider information whether this is on track or not? Because end of 2021 is approaching very fast.
No, it's 2023.
No, but the 127 qubit.
I'm sorry, how many qubits?
So this year, they want
yes, okay, the roadmap and the 127 qubits.
Yes.
I'm afraid I don't have this information. I think they are advancing. I mean, last year, you know, I was thinking because of COVID, you know, they would slow down, that there would not be really any progress, but they got some progress. I mean, in the number of qubits, a new machine that they implemented, in the coherence time that they extended. So, and also, I mean, in the algorithmic space, you know, I was not talking here anything about new versions of Qisit and the libraries for quantum machine learning. It's completely redesigned, and it's now much simpler to do it. So they're working on that. So I would say it should be there. So I don't think that they will hugely miss the, you know, this milestone. So if there is a kind of delay, I think it should be limited.
This is good to hear. Thank you.